Welcome, folks. So in this mobile sensor network problem, I want to explain what you can do that's a little bit more like a if and only if condition when your sensors are in the plane, so not in arbitrary dimensional space across time anymore, and also when the sensors measure a little bit more. So to bring you up to speed, we had sensors moving in time. Here were sort of snapshots in time of the sensors moving. And we were asking if there was an evasion path. And this example has an evasion path because an intruder can evade the sensors, whereas this example didn't have an evasion path because the intruder is always stuck in the top half and then gets caught by the sensors right there. These two examples are really the same covered region, just embedded into space cross time in different ways. So if the only thing measured by the sensors is connectivity data, they're measuring the same information in these two examples. So you can't distinguish if there is an evasion path or not. The extra information that we'll add to these planar sensors that will allow them to measure is pretend they can measure the cyclic order of their neighbors. So let's zoom in a little bit. Here is a sensor. Let's pretend the sensor can measure whether its three neighbors, A, B, and C, in counterclockwise order appear as A, B, C, or whether they appear as A, C, B, which would be the case down here. So at the bottom, I would measure the cyclic order of my neighbors as A, C, B, whereas here, I would measure the cyclic order of my neighbors as A, B, C, which are different. Right, so we can now tell these two examples apart. This is not unreasonable information to assume sensors could add. Pretend, a sensor is like a radar tower, so it's spinning already. And we're not measuring precise angles. We're not measuring the angles between A and B, just this weak ordering information. So how do we take use of this extra information? From the cyclic ordering data, which we're assuming we can measure, you can recover something called boundary cycles. Don't think boundary cycles coming from homology. How do I recover a boundary cycle? Start with a directed edge, use the cyclic order information at this sensor to get the next directed edge. Then use the cyclic order information at this sensor to get the next directed edge. Then use the cyclic order information at this sensor to get the next directed edge. And so you can use the cyclic order information to sort of connect directed edges together to form a cycle. And same thing here, inside the square, you'll get this loop of directed edges. And similarly for this bottom component, and even for the outside of the fence sensors, if you like. So this cyclic order information is something that the sensors can measure, and it gives us this nice global information of what are the directed edges in these various boundary cycles, which we care about because these boundary cycles correspond to holes where intruders might be living. So we'll be able to track holes as time changes. So our theorem is the following. In a planar sensor network that remains connected, so it never splits up into parts, the time-varying alpha complex, which I'll describe briefly, when equipped with this rotation information, the cyclic ordering, determines if and only if an evasion path exists or not. What is an alpha complex? So the check complex has a vertex for each sensor. And then when two sensors overlap, it has an edge. And when three sensors have a point of triple intersection, you have a triangle. Okay, so that's the check complex. For the alpha complex, you have to do something different. Take the balls that determine each sensor, but intersect the ball with what is called the Voronoi region, okay? So if I have a collection of sensor locations, the Voronoi regions are just the points in the plane that are closer to that particular sensor than to any other sensor. So for this sensor, it has this Voronoi region, which is all points in the plane that are closest to that sensor than to any other sensor. Given that we're in the middle of the COVID pandemic, it's worth saying Voronoi regions have a history in public health. So I think it was a cholera outbreak where an epidemiologist or data scientist mapped the wells in the city and then drew these Voronoi regions and also mapped the infections of cholera. And this data scientist found that all of the, or most of the, maybe not all, but most of the cholera patients were in this particular Voronoi region. And he hypothesized that they were all going to this one well that was closest to them to get their water. So he broke the handle on that well, and we learned a little bit more about public health. I've distracted myself. So the alpha complex, you take each sensor ball, you intersect it with the corresponding Voronoi region, you get this bubble-shaped region, and then to build the alpha complex, you look at the bubble-shaped regions. So if two bubble-shaped regions intersect, then you add an edge. And if three bubble-shaped regions have a point of triple intersection, like these do right here, then you add in the triangle. And you'll notice that the check complex can have crossing edges because, you know, here are four balls that all pairwise intersect. But the alpha complex won't have crossing edges, is one property of the alpha complex. So maybe this example here is clearer. So here we have crossing edges from four intersecting balls, but in their bubble-shaped regions, two of the bubble-shaped regions, sure, they intersect, but that means that the other two bubble-shaped regions don't intersect. And so we're missing this edge in the alpha complex. Why do we want the alpha complex instead of the check complex? When you have the rotation information on top of the alpha complex, you can faithfully trace out these boundary cycles. So take a directed edge, use the rotation information to get the next directed edge, use the rotation information to get the next directed edge, etc. And you trace out these cycles that correspond to holes that use the fact that edges weren't crossing. In the check complex where edges cross, if you try to trace out the same information, you use the cyclic information to get the next directed edge, use the cyclic ordering to get the next directed edge, use the cyclic ordering to get the next directed edge, and then you use the cyclic ordering to get the next directed edge, and you cross over into this other hole. So your boundary cycles in this check complex are a little bit nonsensical. They don't correspond to holes, which is what we are going to leverage with alpha complex. So how do you proceed in this theorem? So pretend we had the alpha complex so that there were no crossing edges. You just trace out these boundary cycles. And as time changes, you can keep track of which boundary cycles may contain an intruder, which we'll label in green, or which one necessarily can't contain an intruder, which we'll label in gray. And you know, when this single boundary cycle merges or splits into two, the two boundary cycles both get the green label, because if an intruder could have been in this boundary cycle, then it could split off into either new boundary cycle. And when these two boundary cycles merge, right, so these two boundary cycles were formerly disjoint, but now they merge, well, it inherits the label of yes, it may contain an intruder, because the intruder coming from either spot could now be here. And if you maintain the SYN labels on the bottom, you'll find that you can't have an intruder at the end. The connectivity assumption is crucial. Here's a picture where the sensor network becomes disconnected. And even this alpha complex and rotation information is not enough because the intruder's here, and then the intruder gets released. The intruder could go inside this rectangle, and then the intruder wins. Whereas here, the intruder gets released, but can't go inside the rectangle. So the intruder's still over here. The intruder's outside the rectangle, looking in, and then sensors flood in from the boundary, and the intruder gets caught. So you have to assume that the sensor network always remains connected if you want to be able to do something without GPS coordinates. Because really the only difference between these two examples is, does this rectangle go to the left side or the right side of this dividing line? And it's a nice open question. It's a theorem that with the alpha complex and rotation information, you can decide if and only if an evasion path exists. Nobody knows with the check complex whether the check complex with rotation information is enough. So I would love to know how to do this, but we don't know how to do it. All right, I will end there. In summary, the check complex or the alpha complex alone without rotation information can't determine whether there's an evasion path or not. When you add in rotation information, the alpha complex suffices, unknown with the check complex. But we'd like to be able to use the check complex instead. It requires much less geometric information than the alpha complex. It's sort of unrealistic to assume that sensors without GPS devices could even measure the alpha complex because there's so much geometric data there. So that's a downside of this theorem. You'd like it to work with check complexes, but we don't know how to do it. Any public questions? Thanks so much.